have gotten a message from me that says, that's asking some questions, please just use Canvas to reply to those. You know, it may require you like adjusting your write-up, or it just may just be that, for mostly, you just need to answer those questions and we should be good. If you haven't heard from me yet, you will really soon. I'm trying really hard. And yeah, hopefully, you know, within the next couple of days, everybody will have some response from me on the proposals. Any questions about those? Okay. Any other questions before we get started today? All right. Well, let's keep going. So we're still in the generative kind of section of the course. We're going to recap GAMS real quick, add a little bit more to what we learned, and then we're going to talk about some related ideas in self-supervised learning, contrastive learning, metric learning, these kinds of things, and that will be the subject of today. So, so GAMS, we talked about them last time. They're pretty interesting. They can generate very high resolution images. They have these two. They're trained very differently. They're very different from, you know, the typical network in the way that they're trained, where you have two networks that are kind of playing a game against each other. And you know, the generator network can generate images from the latent space. The latent space, the values in that latent space, like the vectors in that space, those features represent some kind of factors that generate the image. Sometimes you can figure out what those, like after the fact, you can kind of figure out what they control. Other times you can actually do you can adjust the losses or like the losses involved here to get some alignment with features like within the image set. Oftentimes this is done with like faces and, you know, features of faces and things like that. But so you have this great generator, and then you have this discriminator, which, you know, can be a very interesting tool for determining whether something is within the data set of interest or not. Remember, you had this really interesting objective function that we needed to optimize. Because we're playing this game, it's actually posed as a mini-max problem, so we're minimizing something and maximizing another thing. We talked about how we do this, alternating between gradient descent on one set of parameters, gradient descent on the other. We talked about how actually the way that we do this in practice is we make these two gradient descent problems just by adjusting the second part of this objective function. Just this whole thing here takes up values between 0 and 1. So, you know, minimizing is taking us to 1. If we instead of having this be 1 minus that, we just have that there, then we're trying to go to 1, so maximizing it makes sense. Anyways, this makes us, you know, for more stable training, but the training itself is very unstable. In general, it's hard to get right. You know, the tuning of the hyperparameters is something you have to pay attention to. This is some pseudocode for just like how, you know, these things are trained. We kind of talked about it, but here's you know, here's in words what this kind of looks like. Right? For every training iteration we go through, we are going to so for k number of steps, we're going to sample some noise. This is from our noise prior. This is the distribution on our latent space. You know, it's a uniform distribution or a Gaussian distribution. So that gives us our samples that we're going to transform into fake or generated images. And then we're going to actually sample some data from the actual data set of interest. And, you know, notice I'm not calling it the training set because, of course, we're training on both the real data and the fake data. And we first update our discriminator so that it's nice and good on the generator, and then so we do that with the fake samples generated from these these samples from our latent space and the real data. So our discriminator needs both, right, and we label them 0 and 1 respectively. And then when we go to update the generator, we use the discriminator, how it's, it's like its current settings, like its current parameter settings or parameter values. And then we update the parameters of the generator, again, for some sampled noise, like this is your mini batch here. And we just go back and forth doing that, hoping that we converge to something that works well. Yeah, so these things about like how many steps you take for updating the discriminator, updating the generator, are hyperparameters to be worked out. This is kind of like the training the plain vanilla GAN, so to speak. There's a lot of other ways of training GANs, like this Wasserstein GAN. So there are adjustments to the objective that help to stabilize the problem, but it's still, even using those, it's still a fairly unstable training procedure because, again, fundamentally you have these two networks competing against each other. We talked about like the kinds of images that, you can generate. You can interpolate between data points through the latent space, which is kind of fun. This is sort of interesting. So like what does this latent space learn? Like how do you think about that? Well, again, you could try to interpret the features, but some work on this has shown that certain GANs can learn some interesting properties. So we have here some samples of women smiling, of women who are neither smiling nor frowning, and then some men who are neither smiling nor frowning. So if we average these, right? So a bunch of these samples. If we have a bunch of samples of women smiling, and then we average their latent representations, that's going to be something near the center, hopefully, if this is working, of a sub-distribution within a distribution that is generating images like this. And this is true for each one of these. It's going to give us, averaging these is going to give us kind of a different vector, a different kind of locus in the latent space. And somebody at some point thought to do some arithmetic here and said, okay, well, what if we do something like this, where we take the vector that kind of represents the average woman smiling, again, learned by our GAN to transform there, and we subtract from that the average representation of a woman who's neither smiling nor frowning, this neutral woman as it's written up there. So what could that difference represent? Well, if you think about it in our latent space, this is a vector pointing from the mean of the average of a neutral woman to the average of a smiling woman. The difference between those is a smile, right? So one might think, well, maybe that direction has meaning in the latent space. Well, how would you go about probing that? Well, what happens if you take that vector, that's like this displacement between these two averages, that's pointing in a direction that's like going from a neutral face to a smiling face. What if we added that to the face, to the average representation of a neutral man, or neutral man sample, so neither frowning nor smiling? One might expect that if we now take samples near this vector, right, with this minus this plus this, that we might generate faces of men smiling. And indeed, for a number of, for certain kinds of GANs, this actually occurs. And it gives you some kind of understanding, even though this is sort of like emergent and doesn't have to be the case, but sort of makes sense if you think about how the GAN is learning to organize the factors, or use the factors of the latent space to generate important features of the data set. So in data set of of these faces, things like like smiles and not smiles, like colors of eyes and hair, gender qualities and things like that. Like these are all things that it's having to learn how to generate, and it's using some of the features in the latent space to encode those things. And so apparently for some GANs, this is a very useful thing to do, right? If you think about it, it's like a very compact thing to do is to think about features as being displacements from taking you from a certain feature set to another feature set. And that's what you see here. And that's a pretty cool just like emergent property here. Here's another one. We have pictures of men with glasses, then without glasses. So the difference between those averages ought to be something about adding glasses to an image. So now if we take an average representation, here of women without glasses, and then we start to generate from nearby there, we get women with glasses. So these features, the way they're being encoded in the space is not necessarily as like think this is like a displacement in the space. So it's not necessarily like along a single feature dimension, right? So like you're changing one entry in your vector and everything else remains the same. This is going to be probably changing like all the features all at once, but in a particular direction. So kind of cool observations. As I mentioned before, GANs of course were super popular for a long time, and they've been used to do like really kind of fascinating, cool things. Some of my favorites are things like the cycle GAN, which is a kind of like stylistic. You can see some of this up here as well. This is like it's this really clever way of kind of putting two GANs together to transfer the styles from like one image to another one. And you can see here, you have an original horse image that, using this kind of two GAN system, can preserve pretty much everything about the image except for the style of the horse, which is getting these zebra stripes. And there's lots of fascinating examples that are like this, and the more you play around with this, the kind of more fun it can get. A lot of like fun little applications can be done here in terms of like transferring style. There's some, you can go and look at some of these things even online. You can like draw, you can like sort of sketch things out, and then the GAN will use that as like a kind of like a seed or like a beginning state to then generate something that's more in the style of what it was trained on, say like, I don't know, fancy accessories or things like that. You think this can be kind of interesting too, right? Is to say like generating like satellite imagery from some very sparse representation of like the landscape. Anyways, lots of really cool applications for GANs. You can imagine even doing things like text to image or even image to text. In fact, GANs aren't being used now for all the image to text stuff, but other related generative models are. So anyways, lots of cool stuff there. Oh yeah, I should have that video going. Sorry. So not only was this doing a transfer of the imagery, but like the whole or from frame to frame, but for the whole video here. Pretty cool. All right, so we talked about pros and cons last time. We don't need to go through it again. So what more can be done here? So we learned about different generative models. We learned about VAEs and we learned about GANs. So researchers are sitting around wondering what their next research project might be, and they go, hey, let's try to put these things together. So so there's this idea that actually works quite well, and it's called an adversarial autoencoder. So remember what the autoencoders are about, right? The autoencoders are about encoding a data point, so an image, into some latent representation, and then supervising these factors by forcing the reconstruction of the original image from those factors. And the variational autoencoder makes this a probabilistic model where what the encoder actually is doing is producing a mean and a covariance matrix for a normal distribution, then we sample from that. And similarly, the decoder produces a mean and a covariance matrix for a normal distribution, and we sample from that. So we really have, we have a distribution here, some prior on the latent space. Often this, so the VAEs, remember we talked about this being just like a typical standard normal for just because it makes that space really interpretable. But remember that there's a distribution here. We're trying to match a distribution. Well, that's exactly what GANs are doing, right? GANs are about, like the discriminator is about, so the generator is about generating a sample from a latent space, and then the discriminator is about matching or not matching distributions, right? Like it's about saying, are you in this distribution or not? So the way that adversarial autoencoders are put together is you have a VAE, but you supervise you enforce or constrain the distribution on the latent space, not by this KL divergence, if you remember that from the VAE loss, but by generating a sample from the data set corresponding to the latent factors here, and then using a discriminator to try to train that generator to do exactly what we saw before, match the distribution that we want. So if we want these things to come from from particular distributions, if we want these things to match, say, like a standard normal again, we can force that with a GAN construction. And so adversarial autoencoders are AAEs, not VAEs, but AAEs. Were proposed. There's lots of variations on this as well, but pretty cool ways to extend autoencoders, and in particular, there's like a really, as usual. What this can make a lot easier is using different priors on your on the latent space. So here's the typical thing, right? Is to use a kind of use a standard normal distribution. This is for MNIST. What this is a coloring of is this is the latent space, and then the class corresponding to the image that's been embedded in that latent space. And the thing you're seeing here is that adversarial autoencoders, again, because the whole way that the adversarial way that these things are trained, do a much better job of being able to match distribution. They're really good at matching complex image set distributions. So they're particularly good at simple distributions, like having all of this match a 2D standard normal distribution, whereas the variational autoencoder is trying to do that with the KL divergence and doesn't do nearly as good of a job. You see how this is just kind of like splotched, or it's kind of like stretched out in different ways, whereas this looks like what you'd expect to see for a 2D standard normal. And then you can kind of go more wild and say, what about other kinds of priors? What if I know that there's 10 classes here? Maybe I can try to make this, maybe my prior ought to be that I actually have 10 Gaussians here, a mixture of them, and I want to match those, and so like, the prior here is being these like 10 sort of elliptical Gaussians, and you can see that the shape of this looks better, even if like we didn't actually use these to do one for each class. And you can see how this is more like just a big mess. By the way, let's just stop and kind of pause on this. So hopefully this is making sense. Please ask questions if it doesn't. But think about what was attempted here. So our data set MNIST has 10 classes. We're taking images from those classes and we're embedding them in a latent space. it kind of makes sense to say, well, why don't I give the latent space the distribution on that latent space some kind of structure that matches like 10 classes. So here being 10 Gaussians, right? And one might hope that if we just do that, that you see that, you know, all of the images for, you know, for the number 1 are in one of those Gaussians, and all the images for number 2 are in another Gaussian, and so forth. But that's not what happened here, right? So why not? Why didn't that happen? Yeah.
Some numbers overlap features, like 8 has some features
Yeah.
like 6.
Yeah, perfect. Actually, that's exactly right. And it also has something to do with the fact that the way that they arrange these Gaussians is they sort of share a common space here in between them all that allows for that fact to happen. So notice that, you know, the like the many of the interfaces between the classes actually happening here, you know, in this intersection. Although you can see some of these classes, it's not quite that clear, but it's exactly what was just said. If you go and look at the boundaries between these kind of class regions, you will find images that look like, you know, both classes essentially, right? Like a 1 that has kind of a longer top to it, that looks like a 7, or an 8 that kind of has a narrow top that maybe looks more like a 6, and so forth, right? So unless you explicitly force it to use those, you know, those Gaussians within the latent space to be only for the class, and that would have to be you know, an adjustment to your loss function, it's going to use that latent space in the best way possible to, you know, to lower its loss, to meet its objective. So just goes to show that, like, you know, if you want something to happen, like the construction, expressing that in an objective can be really challenging. Anyways, these are very cool.
I had a question.
Yeah.
I'm still a little confused on, like, these images are shown a lot. Like, what is the 2D representation of that is always confused me. Is like each axis like?
Yeah, good.
Space?
So yeah, right. So this is the latent space, and what we've chosen. So one of the hyperparameters, and always in these problems where we have a latent space, is how many dimensions will there be? Because it's latent, we don't know how many dimensions there should be, but we have to, you know, for the network to be trained, we have to pick something. So you might pick 2, you might pick 100, you know, you might pick something else. In these examples, 2 dimensions were picked.
Okay, so there's just 2 unknown dimensions. You go
2 latent dimensions, 2 hidden dimensions.
Dimension.
Yeah, like this, you know, this is Z1 and this is Z2. The 2 entries in that latent space.
But in like the GANs, you're sampling from more than 2 latent spaces.
Yeah, typically like with, you know, when you want to generate images, you will typically the dimension of the latent space will be much larger, because you expect that you need far more factors of variation to be able to accurately reconstruct an image.
And is the idea of like one latent space for like faces would be like, oh, this is like eyes?
Well, yeah, that's kind of like, that's the point of this right here, I guess, is that the features don't necessarily end up being like, you know, like the entry, like the first entry corresponds to, I don't know, like how the left eye looks, and then the next one. In fact, that's definitely not what's happening here. There are ways to force this by like aligning the features with certain known information, so it makes it more of a supervised problem. But in these like purely unsupervised settings, you know, you can't force that, and it almost always it will not do that, because it ends up reconstructing these things in far different ways. And one of the ways you can see that is, you might think that like glasses is going to be like some kind of discrete, like single feature. Maybe the last feature in the vector is like how dark how dark are the glasses. But really, in reality, what it is like there is this dense vector, meaning like it's crossing all of the cardinal dimensions, and it's it's moving in that direction that causes in the latent space, that causes the generator to generate images with glasses. So it's not, if you think about it, it's like, I'm going to chalk here. So it's not like, moving, this is again in 2 dimensions. It's not like moving in the Z1 direction or the Z2 direction gives you glasses. It's more like moving in some combination of those dimensions gives you glasses. So like, what does that, what does that mean? That just makes it very difficult to interpret the latent space, except through like, kind of like fortuitous studies like this. So that's, that has spurred a whole bunch of research into, well, what, if I do have some additional information, how do I build that into the latent space? Good question. Did you have other questions?
No, thank you.
Okay, cool. Yeah, so these are adversarial autoencoders trained with a 2-dimensional latent space. And this is the prior, like the distribution that we want on the latent space, in that 2D latent space, is a single standard normal. And here, there's 10 of these kind of elliptical Gaussians. Good. Yeah?
Why did they choose just 2? Why did they have a little larger?
Oh, this is because we can visualize it.
Well, you could have a larger dimension than just use PCA, TSV.
That's true, but you'd be losing information, right?
Right.
So this is meant to be some kind of like, very like no lossless representation of the latent space. But yeah, you could run this. You could run the same example on your own and change the latent spaces, and you could choose to like do PCA and take a look. And I mean, you get very similar, kinds of representations, but yeah. Okay. Yeah. In fact, here is a way to do this so that you do force the each of these Gaussians. So if you do have the additional label information, which like in MNIST, you do, you know your sets of zeros and ones. The way that you can build this information into this network is quite simple. You build it into the generator, or into the latent space, well, to the latent representation that the generator uses to generate a sample. So what is happening here is, I embed an image, I encode it and I decode it. That's what I'm trying to do with my autoencoder piece. But then I'm also trying to match a distribution here. So let's say we have this in 2 dimensions again. We have these 10 Gaussians. Now here I say, okay, when I go to generate this, I'm going to make this a class conditional GAN. And the way that I do that is I say I add some features to the latent space. So I have this representation that's coming up here, and then to that I add basically like a 1-hop vector, where the entry corresponding to the class is going to have a 1, everything else is going to be a 0. So I'm actually telling the generator which class to generate. So it's going to learn to do this, right? So it's like it's going to learn that it's going to take this information, it's going to take this information, it's going to give me the 1. It's going to reconstruct me reconstruct me the particular the Gaussian. So what does that mean? Well, if I have this class information here to do that, this no longer needs that information, for instance. So you can separate, like, in some sense, like style from content, and you can tell you can force the latent spaces to say, like, okay, well, put all my 1s in here, all my 2s in here, my 3s in here, and so forth, using that construction, and get this kind of alignment. So notice that this is still trained in like this unsupervised way, but you have this, you're giving it class information. So it's sort of supervised because you're giving it additional information that tells it like something it if it needed, it would have had to have worked out on its own. And here's just another kind of goofy example, like, what if you forced your latent space to look like this like logarithmic spiral? How would it use that latent space to do that? Well, you know, it can use it like that, yeah.
What label do you send it if it's being given an example from the simple counts instead of an example that was just coded by Prof? So like if it's being sent a, I guess in this case, positive example.
Oh yeah, so like, or just like if you just chose something from here.
And the other way around, what label, if you're drawing an example from PC and then you're sending that.
Yeah, so that's what this is, drawing example from
yeah.
PC.
Cool, yeah.
And then like, well, what would it decode to?
What label would you send it in the one hot vector if you're anything?
Yeah, this is great. So you give it, if you want a 1, you give it a 1. If you want a 2, you give it a 2, right?
Okay.
Right, so like that's why this is class conditional. It's like, what it's learned to do is generate, you know, samples from your data set, but it's learned to do this conditioned on like which kind of thing you would want. Right, in this case, in the simple case of NNIST, you have these labels, and so it needs that it needs that information, and then it says, okay, I'll generate a 1, or I'll generate a 2, or 3. So again, content and like style. So by adding that information in there, it allows this latent space to only focus like on style, and then uses this feature, these features right here to decide on like which content. And so you get things like like this right here, where you have these are both generated with the with Z1 and Z2 being the same, like it's the same. The axes are exactly the same, but we said, okay, generate 0s and generate 1s. And notice how, if you look at the corresponding positions in each of these matrices, you get the same style of digit, right? So like, look at the bottom corner here. You have a 0 tilted to the right, and then you have a 1 here tilted to the right, and then I don't know, if you kind of like go up this column here on both sides again, you see that the 0 on the left side, the 1 on the right side are like standing up as you move upward. As you take Z2 and you move it upward. That's not true like all the way through here. I mean, somewhat is, but notice that when we're over here, I guess it still is tilted a bit to the right, but not nearly as much, right? So, but anyways, that's the point is that like which type, like which class we get, we determine by telling it, say, give me a 0, give me a 1, but how that 0, that 1 gets drawn is dependent on which values of Z1 and Z2 we choose. So it's cool, like this gives you like this whole like set of tools for, I don't know, shaping how you want your generator to generate, things like how to use the latent space. You're using additional information to give remove the burden of learning that information. So it's it only learns that the other information that's not part of that particular code. Okay, yeah, you can continue to split up these ideas of style and labels. Lots of interesting things you can do. We need to move on to the next part here. Any questions before we're going to move on from GANs actually at this point, and variations on those. We're going to go to a new topic called contrastive learning. So any lingering questions on GANs? Yeah.
Are there any heuristics about using certain distributions? Like what if you have extremely class imbalanced data? Is Gaussian still fine? Or?
Yeah, I mean that's a good question. I actually don't. I don't really know. Like these things. It's a good question. I don't know the answer to that. I don't know. I'm not sure. Like it would still work, but it would probably it may not be so like clear. Like this may not you know, this kind of like direct alignment may not happen. But I don't know. It seemed like a fun little research project. Good question though. All right. So contrastive learning. All right. So we're going to start with kind of an older supervised idea for contrastive learning, then we're going to get into self-supervised, so this kind of under this unsupervised umbrella. So an interesting problem in computer vision, which can be absolutely abused, is this idea of facial recognition. You know, being able to look at an image and be able to recognize that this face corresponds to a particular person, no matter the pose, or even, you know, things like the time period, or I don't know, like all kinds of other ways in which images can vary. So, you know, we have one of the greatest actors of all time, Brad Pitt, here. And the many, many different roles he's played throughout you know, his illustrious career. So this is great. This is great if this is a somewhat easy problem if what we have, if what we want to do is recognize the faces of a small group of people, right? Like if, I don't know, you have just images where there's only ever like 20 people in those images, you can take the techniques that we've learned and just train up this kind of straightforward classifier to, you know, to say, well, you know, this is one of those 20 people, even if it's like 100 people or something like that. But this problem becomes really challenging if what you're trying to do is recognize the faces of thousands, tens of thousands, hundreds of thousands, millions, keep going, you know, like. And we use facial recognition as like a way to motivate this, but in general, you know, anytime where you have a very large number of classes, and especially if like those classes are open in the sense of like facial recognition is like this, you know, we don't expect to have seen every single face. You know, people are being born all the time. There are new faces entering the world. So it doesn't even make sense as a classification problem because we don't have all the classes, you know, like as labels in hand, right? So, so how do you go about a problem like this? You can't just go and solve this with a straightforward classifier as we have learned how to do. I do want to just call it one more time that like facial recognition is used or is abused, has been abused in many different ways, and does pose a danger to like, you know, like free and democratic society. So, in all of this, in teaching this, this is a problem that's, you know, that exists and makes sense and is well motivated, but you know, proceed with caution here. Don't please take the things that you learn in this class and go build a face recognition system that would abuse, you know, the capabilities here. How would you go about doing this? So we need to change the way that we're thinking about this problem entirely. What if we have too many labels? The set of labels keeps changing. So a really simple thing to do here is think about what a classifier is actually doing. A classifier, remember, we have this like whole network. You know, takes in an image. It's progressively through different convolutional networks or convolutional layers is like transforming that image into different feature maps, and then eventually, you know, you get to this fully connected, these fully connected layers where you have now a vector representation of your image. And eventually, this is going to go. There's going to be a linear layer where you're going to multiply this matrix, which is going to be, you know, number of classes that you care about by the number of features, and that's going to be basically a bunch of dot products with like the rows of this matrix. And the rows of this matrix, those represent, you know, they're parameters that we're learning, but each of those rows represents kind of like a prototypical or standard representation of that class. And when we do a dot product with our embedding, with that representation, are embedded with that representation, you know, what we're hoping is that the dot product with the correct class representation is highest. That means it's most aligned. More aligned with that class representation than any other class representation. What does that mean in practice? Well, that in some sense that's like when, you know, as we adjust, you know, all the parameters in this network, we're trying to increase the score there, which means like greater alignment of our embedding at that layer with the class representation. So there's a kind of like, putting together of like, you know, a stereotypical or a prototypical representation in our embedding. At the same time, we're also doing dot products with all the other class representations, and you know, the other way that we can make this dot product the largest of them all is to make sure that we have a smaller dot product with the rest of the class representations, right? So that means that these, you know, like the angle between them is growing greater, you know, getting more and more towards like 90 degrees, in which, you know, the dot product is 0, and we have a 0 score. So if you think about that kind of like abstractly, what's happening is that and remember, this is happening for all the embeddings of that class. So like all the images of a single class, their embeddings at this layer are being kind of pushed towards this prototypical representation, and therefore being pushed towards each other. So what's happening is that we're taking representations, taking these embeddings, and we're pushing like all the ones from the same class together, and simultaneously pushing them apart from embeddings from images of other classes. So can we do the same kind of thing, but without setting this up as a classification problem, or you know, a problem where we're using cross entropy to maximize the likelihood of the correct class score? And the answer is yes, and that's what metric learning is all about. So metric learning has, you know, a bunch of different, you know, kinds of architectures that one might use, and like the first simplest version of this is what's known as a Siamese network. It's a bit of an unfortunate name, but it's kind of stuck. And the way that this works is simply you take two images from the same class, you use the same neural network. So like this looks like two different networks, but it has this like W in between. This just means that like these networks share the same weights. It's the same network. And we're going to use this network to embed or, you know, encode or represent this image as a vector. Same network, we're going to take this image and we're going to represent it as a vector. And now our loss is going to be literally to take the, you know, the difference between these, or just any distance function, and the loss will be to minimize, the objective will be to minimize the differences between those embeddings of the same class, right? So, you know, the way that you do this is you sample, you know, pairs of images here for the same class, do this for a bunch of different classes, and, you know, you have these contributions to your loss from each of those pairs, and then you minimize that. And that's called a Siamese network. This is you can do that directly, or what you see more often here for metric learning is that you use this hinge loss. If you think way back to the beginning of the course, we actually talked about this loss here, this hinge loss. And the idea here is that you have this margin. This M right here represents a thing called the margin. You might remember that from the beginning class. And the objective here is a max between 0 and the margin minus the distance between our two embeddings from different images of the same class. And so what does this mean? Well, you know, it's the reason why we call this a margin is that this is allowing for the distance to not necessarily be forced to 0 once it's within a certain margin, that the contribution to the total loss is 0, right? Once this distance is small enough, then the loss. Wait, hold on a second. Or does that seem wrong? Yeah. What I'm saying is right, but this seems, as I'm looking at it, seems wrong. Yeah, this is like reversed. It should be, now I feel really, like I'm really not sure. Because this should be right, but it seems wrong. We want the distances, like once they're close enough, we don't care to minimize those anymore. Like we'll use the rest of the capacity of the network to minimize other things. I'm sort of like confused by that. But we're gonna blow past this here and get to the next set of networks because there's a problem here. Anybody spot it? This has a trivial solution that is problematic. Yeah.
Just for the same class, just predict the same representation for everything.
Yes, and actually that's good. That's kind of like what you're wanting. Within a class, everything's the same.
Every single class do that?
Yeah, like if what happens is basically like what this can kind of like collapse to learning to predict just a constant vector for all the classes, right? Everything will be as close as possible to each other. It seems like we've learned something, like it meets the objective, but we haven't learned the right thing. Because what we haven't taken into account is the fact that all we've done is push the right things together. What we haven't done is we haven't done any pushing apart of embeddings from different classes. So how do we prevent that? Well, it's as simple as adding in one more term in our loss that is keeping track of negative examples, so pairs where the images are from, or the embeddings are from from images from different classes, and making sure that those are pushed apart. And this is where we get to what's called a triplet network, and it's called triplet because we're going to have three images. We're going to have what we call our anchor. We have our anchor image. We have our positive image and our negative image, or the same image and a different image. And what these are all is all the same neural network. We're going to create embeddings for each one of these, and then we're going to compute the distances between our anchor and our positive example, and we're going to compute the distances between our anchor and our negative example, and then we're going to set up our objective so that we minimize the distance between, we minimize this distance and we like maximize this distance, or we push it outside of a particular margin, which is what that loss was in the last slide was actually referring to. Was actually on the negative side of that, but never mind. Don't look at it. Maybe I'll fix it after this and just concentrate on this, because this is Siamese networks are bad to use because they have that collapse problem. Here you're preventing the collapse by by having examples where you do want there to be a difference between the embeddings, and you're pushing those away. So a constant solution here doesn't work because that here that will incur a lot of penalty. And the way that this looks here is we have a term that we want to minimize for our anchor and our positive or same example, and then we have a term here for our anchor and our different or negative example. But notice that there's a minus sign here, and notice that we have a margin here as well. It's alpha, not m, but it's playing the same role. And so we want to make this as small as possible. If we make this as small as possible, that's a problem because this will get to 0 and we'll have an alpha here. So what we want this to do is to be at the level of alpha or greater when optimizing, and that's why you have the minus sign and then you have that margin added there. So this is the formulation for a triplet network, and it works great. This is a very common setup for learning representations of your data, where you do have classes, but maybe you have too many classes, or the actual classes might change as you say, like, go to run inference on these, meaning like you go to do, like there's not like really predictions here, right? But when you go to like compare embeddings for images and say, hey, is this another Brad Pitt image, or is this an, you know, Angelina Jolie image or whatever? And yeah, it works great. Let's see, how are we doing on time here? Let me just keep moving on here. So there are different versions of this, of metric learning ideas. There's actually lots of them. This is like the standard kind of classification loss, right? So like this is when we're optimizing for you know, our classifiers, the setup looks like that. This is a triplet loss, the thing that we were just looking at. We want the difference in distances between, you know, our positive examples and our negative examples to at least be of the size alpha, this margin. And there are other formulations of this. So there's things like the center loss that that do try to learn a kind of prototypical class example for every class, but the way in which it's done is not via, you know, the softmax cross entropy loss, but you know, you're minimizing a distance between these. The details of this are a bit complicated. We're not going to get into it today in this lecture, but there's lots of ways of doing these, and all of these come under the name of metric learning, mainly because we are using distances or metrics in the losses. Okay, questions so far? Do you see how? Yeah.
Are there different distance metrics that
Yeah.
are used with these?
Yeah. I mean, everything's here shown with like an L2 distance, but you know, any kind of distance will do. You know, like they'll give you different geometries for your, you know, your embedding space. But yeah.
Does it depend on the task that you want to do eventually?
Yeah, kind of. Yeah, kind of like, yeah, it definitely does. But it's kind of, yeah. So like there are things called like focal losses that are kind of like this, but will have, you know, different exponents here depending on the class, as a way of like dealing with class imbalance and things like that. I don't know. There's like all kinds of stuff. So again, like we're not even covering 1/100th of all the stuff in deep learning, but you know, here's some of the core ideas. This can get even crazier, and in particular in face recognition, there's a lot of like losses that are known that are called things face because they were developed in face recognition. So sphere face, cos face, arc face. They all look like the softmax losses. If you go back and look at, oh, I guess I have it up here. Like here's your softmax loss, and it turns out if you just know your math identities, that you can write these dot products, you know, as the product of the length of the two vectors involved, and then the angle that's made between them. And there's like this bias term out there. And why is that interesting? Well, you know, you can do a bunch of different things. So like, one thing you might decide to do is to say, well, it doesn't really make sense. Like, all I really want to do, like when I'm making these dot products, when I'm doing this dot product, I don't really want the length of that vector or that representation to like be factored into the, you know, the score. So you can do things like, you know, constrain those rows to have length 1. So, you know, what you have are just classes on the sphere. And this is why this is called sphere face, because really what you're now doing is like, you're really just comparing angles between things. Like strictly, you're eliminating at least part of the contribution of the length of these vectors. And then you can build in margins. And so like, this builds in a margin on the correct class, which like if M is large, it penalizes to a greater extent the larger angles made between the correct class and the embedding. So like that's softmax. There's something very similar for the, sphere space. So something similar for the curl space. Something similar for arc face. Arc face is really interesting. It goes all the way and says we want everything. We want both our prototypical class representations and our embeddings to have length 1, so everything's on the sphere. We're only looking at the angles then between things, so we really are on the sphere. And then we penalize not by multiplying by margin, but like adding a margin. And then there's some sort of scaling factor. So again, not to get into details here, but the reason that these kinds of adaptations of the losses were introduced is because these give much better results in terms of like being able to recognize or like separate large classes of things within a space. So like solving the facial recognition problem, these losses can help learn more classes. This is a little bit more about what arc face looks like. I won't spend much more time on this. Yeah, and then you can like combine all of these together and have all the faces lost. Yeah, you get much better results on like face tasks with these other losses. That's just a table showing that. Okay, what does that mean when you build in margins into the space, into the embedding space? Well, really, what those margins are doing, they're like there's your kind of like typical classification, like the losses on the sphere, or sorry, the classes on the sphere. So like your class representations are in the centroids of these, and then this is the distribution of the classes around it. When you penalize these things with a margin, it's really just tightening up the class representations around, the class embeddings around the class representation. So, you can see how this gets a lot better at classification because, things are embedded really close to here and actually leave space to like be able to learn additional classes in the future and so forth. Okay, so all that was kind of set up to this, which is like a very interesting, current line of research in unsupervised learning, and that is contrastive self-supervised learning. So contrastive learning, what we just learned, it's a kind of supervised learning because we are using the classes to create our mini batches, right? Like we have to have an anchor and a positive example and some negative examples, and to be able to do that, we need to know the classes. So contrastive self-supervised learning is exactly what it sounds like. We want to still do contrastive learning. We're going to like push things from the same class together and push things from different classes apart, but we're going to do this in a self-supervised way. We won't have access to the notion of classes. We want to push similar things together and dissimilar things apart in a self-supervised way. So this kind of stuff is really quite cool. So this is what we just talked about: contrastive learning, positive pairs, negative pairs. That requires labels. What we do in self-supervised learning is to try to do like the same idea of pushing similar things together. But if we're going to do it's going to be self-supervised. We can't use labels. So how do we then figure this out? Well, what we do is we're going to learn representations of these things, just like of these images. But we're going to do this in kind of clever ways. So there's some kind of early work that does things like I'm going to cut my image up. I'm going to give you the different patches. You figure out what the relative locations of those patches are. So it's using a single image. It's cutting it up, and then it's like saying, hey, like let's put this back together in the right way. Kind of like a puzzle, right? No labels needed there, right? It's just like we just use the image, we cut it up, and put it back together. To the extreme, you might actually, you might take an image, cut it up, give it a you know, a permuted like arrangement of those patches, and then ask the network to, you know, give you the correct permutation and put it back in the right order. You might try colorizing an image, you know, give it a grayscale image, and then, or you have a colored image, the input is a grayscale version of that, and then you train to turn that back into a 3-color image. These are all like things people tried, you know, sort of work, but it wasn't really all that powerful. Then, like the group at Facebook AI, or whatever they call themselves now, Meta AI, they started to do a lot of really interesting work and produced a lot of really interesting self-supervised learning methods that don't really look like this. They look like the following. So the question is, how do we do contrastive learning if we're also self-supervised? What we're gonna do is it's gonna look very much like what we just said, or, you know, like the examples we just looked at, but we are gonna cut up the images. We are gonna use like crops of the images. But what we're gonna do is we're gonna push crops from the same image together, and we're gonna push crops from different images apart. So no extra label information is needed. You just have to know that the crops are from the same image and they're from different images. So like, it's self-supervised in that way. What does that mean? Well, what we're gonna do is we're gonna take these images and we're gonna cut them up. We're gonna, you know, crop them. Wait, what happened? Oh, this was supposed to. Nah, it didn't work. Maybe it's just here. Does this work? There's a nice. it's a really nice. Why didn't that work? I don't know. Okay, so this is it right here, but I don't know why it doesn't work today. So, no, this is not it right here. Sorry. This is it right here. So what's going to happen in contrastive learning? That's small. We are going to take our image, and we're going to, let me just go back to the slides and come back to this. We're going to cut the image up into you know, we're gonna crop it in different ways. It could be overlapping, it could not be overlapping. And then what we're going to do, why does this not, I feel like I lost a slide or something, sorry. Then what we're gonna do is we're going to augment this image somehow. So we're going to apply some kind of data augmentation. So this could be, you know, jittering the color, this can be blurring it, this can be like stretching it and changing its, you know, its ratio, the aspect ratio. Whatever we want to do, those two crops, and what we're going to do is we're going to, whatever we end up in the end, we're going to say that that's a positive pair. And then we're going to have done this with a whole bunch of other images in the same batch. And everything else from every other image, that's going to be considered a negative example. And then we're going to train exactly with like the losses that you saw before. We're just going to push positive examples together, and we're going to push negative examples apart. And you might think, like, how can this work? Like, why does this, you know, how does this have any chance of working? Like, won't it be the case that we're going to put in our mini batch, we're not paying attention to labels. Aren't we going to have like 2 images from the same class, and you know, we're going to have different, you know, crops, different augmented crops of those, and we're going to say those are negative examples when in reality they're from the same class. Won't that mess things up? And the answer is yes. If that happened a ton, that would mess up the learning a bunch. But it turns out that in these data sets that we have, like ImageNet, where there's lots of examples per class, you know, when we sample our mini batches, it'll be very rare that we will actually sample two images from the same class. And when we do, it'll just be one amongst many negative examples. And so on average, we expect that to kind of wash out in the optimization, and that the strength of this this pairing right here, or our positive pair for each of the images is going to overcome that, and that is what happens. In fact, there's a number of different methods that do this. And there's even more now that have different different kind of different names that sort of mention contrastive learning or something related to contrastive learning. And what has been found is that that for the best versions of these kinds of models that again are just taking two crops of the same image and calling those positive pairs, taking crops from different images and calling those negative pairs, they learn representations where when you do a very simple linear classifier on top, so literally just putting like a linear layer to transform your embedding into scores, and then put that through a softmax, so you have like what's equivalent to like a logistic regression. That the performance of those classifiers on those features is almost at the level of the best classifiers, the best supervised classifiers. So learning features in this way, this kind of crazy way of doing contrastive learning but doing it in a self-supervised way, you learn good enough features where you're almost as good as just a straightforward supervised classifier on ImageNet. So classification is happening for both, but I just want to emphasize one more time, you have a very shallow, it's called a linear classifier, but it's just think of it as like the last layer in your classifier. You're just attaching that to the embeddings of the features learned from like one of these techniques. And this got like the whole community really excited because if you remember when we started on learning about unsupervised learning, one of the appeals of it is like labels are expensive, and like how learning usually happens. Like you think about like the episodes of learning in your life. Yes, there's definitely episodes of supervised learning, but there's many more episodes of unsupervised learning, and we seem to like through interactions with the world, learn a lot about it, and we don't need labels, and we just learn some sort of like general distribution, and then we somehow use that general knowledge to then do things like recognize objects, and these networks are starting to show the ability to extract those kinds of features without any labels at all. And so it's super promising. There's lots of versions of this now. Like this is now a couple of years old, and there are other better versions that are as good, maybe sometimes even beating these the supervised classifiers, but in general, just represents a really fascinating, interesting direction in which research continues to go.
Just so I understand, do you have to? So you'll take an image, you'll break it up, and then you'll say that is essentially the same image, right? It's part of the same class.
Yeah, exactly. So so classes here really. So you really have like one image per class, or sorry, I should say differently. Each class corresponds to a single image, but you don't have a classifier, so you're not actually like there's not if there's a million images in your data set, you don't have like you don't have a classifier that's trying to compute a million scores, one for each image. You're doing the contrastive part where you're pushing the embeddings of those images together, but they're augmented crops, right? So the crops from the same image, and then they're heavily augmented. So lots of changes to them. So different parts of the image, different crops. This is actually showing like from the same image, so kind of an unfortunate example, I guess. But think of it as maybe like just the snout here, and maybe just like the eye and ear here as the different crops. But like that's your class, and then each of these crops is now compared to all the other crops from all the other images, and those are all considered negative examples. Right, so we're pushing together the two augmented crops from the same image across the whole batch. So each pair is being pushed together in a mini batch iteration, and then all the other pairs are being pushed apart.
And then in the end, once you have, I guess, does someone have to go through at the end and say, like, oh, this is the pit, like, if it's gonna.
No. Like that's not what you do. Like that's the point of these kinds of studies right here, is to say, like, let's learn a contrastive self-supervised, learning method, or network on ImageNet. Okay? So it doesn't know anything about the classes when you do that training, when you do the self-supervised contrastive learning. And then you say, okay, now that we've done that, now let's go back and say, okay, let's take the test set from ImageNet, and let's see how we do using just these learned features from the contrastive self-supervised learning method. Let's just use these features as a representation of the image, and just learn a very shallow neural network, a single linear layer. So you learn that.
So that's
you train that, yeah. So sorry, I said this wrong. You train that on the training set of ImageNet, then you go and evaluate on the test set of ImageNet, and now you compare it to the other classifiers that were learned end to end.
Okay, so there's a little bit of supervised.
Yeah, just so you can do the comparison. But remember, like, think of like the embeddings as fixed. You can think of like the contrastive network as being fixed in that training. All you're doing is training the last linear layer in a classifier to be able to do this comparison.
And effectively, that would be the same as, like, that could be a person. Like, this is just a more sophisticated way. Like,
yeah, I mean, a person could, like.
That's kind of what I was thinking in my head. Like,
Yeah.
Someone goes through and they see.
I mean, the way that you would do it is you would say, okay, like, look, all of these embeddings are clustered together. Now, what do the images look like? And you'd hope to see that, like, over here in this cluster they were all pigs, and over here they were all cars and things like that. But that's a difficult thing to do for millions of images and thousands of classes, right? So the thing that's done here is to just compare with the classification task, but just using the embeddings learned previously by the contrastive self-supervised learning. Good. So it's really cool. So self-supervised, so it's unsupervised, and it seems to be learning features as good as a classifier can learn in terms of like being discriminative for the task. So that's amazing. It's getting even better. You can follow, like I said, like this continues to be like a big line of research at Meta AI. That's it. So